Okay, I'm going to start. So, what we're going to do today is essentially problem solving based on the principle of work and energy, okay, which says that the kinetic energy T1 plus the work done by springs, gravity, friction is equal to the net kinetic energy at a different instant of time. So, this is our first problem. So the 10-pound sphere starts from rest at theta equals 0. So it starts over here and rolls without slipping. Okay, rolls without slipping down the cylindrical surface, which has a radius of 10 feet. So let's call this capital R, and let's call the radius of the sphere small r. Find the speed of the sphere's center of mass at the instant theta is 45 degrees. Okay, yeah, just take a seat. And you're going to be here for like 10, 15 minutes? Yeah. Feel free to be there longer, no problem. You guys looking for a seat? You can squeeze in. There are a couple of seats here in front. I like students to sit in front.
Don't they have to answer questions in the program?
What's that?
Don't they have to answer a question?
They have to answer, absolutely. Okay, so a problem like this is you're going to think, well, do I have to draw the free body diagram? Well, I would say it's always a good idea to draw a free body diagram. In general, when there's a question in which you're asked to find velocities at one point of the motion, and you're told to find that as a function of distance, in this case it's going to be theta, it's always a good idea to think of principle of work and energy. Okay, typically velocity as a function of time. Sorry, velocity is a function of distance or displacement. So in this case, I'll start with the usual thing, which is draw a free body diagram. Okay. So because the sphere is on the cylinder, there's a normal force, and there's mg. Okay, is that it? Am I missing any force? So there's friction because this is rolling without slipping. Okay. Is that it? Okay, what coordinate frame would you use for this problem? UT and UN. It's really optional in this case. You could use UR U theta too, because this is you can also express it as R theta. But you see in this problem, you really don't need to know anything about the coordinate frame. So next, I'm going to use the principle of work and energy. Okay, so as I said earlier, T1 plus U12 is T2, And so let's try to identify each of those quantities in there. T1 is the kinetic energy when it is at theta equals 0, right? Right here. So what's the kinetic energy? It's 0 because it's starting from rest. T2 is the kinetic energy when the sphere is at theta equals 45 degrees. So what's the kinetic energy? 1/2. Okay, now is this a particle problem or this is a rigid body motion problem? You're given the radius of the sphere. When you're given the radius of the sphere, you better think of it as a rigid body. So besides the translational energy, it also has a rotational energy. So half mv square plus half I omega square. Okay. Now the inertia for a sphere, and I'll give it to you, is 2/5 mr square. So half mv square plus half times inertia, which is 2/5 mr square omega square. Okay. Is there a relation between v and omega? So kinematics, because the sphere is rolling, the velocity is omega times r. And so we can simplify T2. So I'm going to shove this in here to get, I'm going to just write the final answer, but you can simplify it later on. So it comes out to be 7/10 mv square. Okay, so we got that, we got this, just missing the work done. Okay, so when you have the work done, that's where you want to look at the free body diagram, because that's going to tell you the work done is due to the external force, okay, and all the external forces are shown in this figure here, the free body diagram. So let's write U12. So there are three forces. There's the normal force, there is friction force, and there is mass times gravity. Okay, what's the work done by friction force? It's 0 because the work done is force times distance moved. Force is acting at the contact point, and the contact point is at rest. It's not FF. This point is moving as a displacement of 0. Yeah.
Forever?
Always true. If it's rolling, yes. If it's sliding, no. When it slides, this will have a non-zero displacement, and then the work is done by the force, friction force. The normal force, what's the work done by the normal force? It's 0 because normal force acts this way, and this sphere is not moving up and down. It's the contact point is fixed. So the only work done comes due to mg. Okay. So mg, and it's basically it's mg times the displacement, right? So it's the distance moved in the y direction from here all the way to here, this distance. Okay, and since mg acts downwards and that displacement is downwards, what's the sign of the work done? It's positive. Okay, so I just need to find delta y. Delta y is this distance. Okay, what is delta y? R minus r cosine theta. No. So let's see what this distance is. What's this distance? Right from here all over there. It's r plus r, right? So it's going to be r plus r. So it's going to be r plus r. It also happens to be this distance. Right? It's the distance from the center of the cylinder all the way to the center of the sphere. And so it's going to be r plus r, which is this distance, minus this distance right here. So that distance is r plus r cosine of theta, or cosine of 45. So that's it. So yeah.
Cosine of 45. Isn't only on cosine of 45?
No, it's r plus r because this thing here is r plus r. This is 90 degrees. My bad. I should probably draw it a little bit more clear. So it is like this.
Okay,
This
so
is 90. Yeah, it's from center because the set. Remember, it's the distance. It's the work done by moving the center from one point to another. So it's the distance from center.
Does it have to be from the center?
It has to be the center. Now, if it's a particle, no, it's r is 0, so you don't have to. There's no small r. So that is mg r plus r 1 minus cosine of 45 degrees. So all that is left is to use the equation 1. So 1 is that from 1, 0 plus mg r plus r 1 minus cosine 45 degrees equals 7 by 10 mv square, and the mass cancels off, gravity is known, r is given, both r's are given, we got to find v, that's unknown. So if you do the math, v comes out to be 11.9 feet per second. Okay. Any questions on that? Okay, so next question. A pendulum consists of a 10 kilogram disc Okay, so let's call that M1 and a 3 kg slender rod. If it is released from rest in the position shown, so it's released from the horizontal position, find the angular velocity when it rotates clockwise by 90 degrees. So at some point of time, this pendulum ends in the vertical direction, and then you got to find what is the angular speed when it is in the vertical position. Okay. So just like any problem, I would highly recommend drawing the free body diagram, even if you think that you don't need to do it. Okay, so forces. Okay, the moment M, see there's a moment M, it's an external force, it has to be shown in the free body diagram. Since I dismantled the pendulum from the hinge, it needs to be replaced by a force in the x and y direction. Okay, is there any other force? Is mg m2g, because I assume that the mass of the rod is m2, and is that it? There's m1g too. m1g, is that it? Okay, so again, for this problem, the reason why I would go for principle of work and energy is because you're told to find the velocity of at an instant of time, and you know that the pendulum travels a certain distance. So in a way, you're told to find velocity as a function of distance. Okay, time does not appear in this question. So when you see that kind of problem, it's a good idea to use principle of work and energy. if however you need time, then you have to go for the acceleration, then integrate to get the time. Okay, so this is a principle of work energy problem. Okay, in fact, some of the problems we did in the last chapter, last exam, you could actually have done them using principle of work and energy. It would have been much easier to do it that way.
In the finals, we get to pick.
You got to pick, yeah, because yeah, in general, I think in this course, if we had solved those problems using work and energy, that would have been fine, unless you were asked specifically, draw the free body diagram, do this. So that way we can influence how you answer the question. So the principle of work energy is this: the energy at position 1, okay, when it is horizontal, is going to be 0 because it starts from rest. The kinetic energy at any instant of time, let's say at a general instant when this angle is theta, okay, so then we can then put theta equals 90 if you want to. So the energy is, okay, now remember last class I had told you there are 3 equations for energy T. It is half mv square if it's translation. If it's half I mv square plus half ig omega square if it is pure rotation. And you could write it another way. You could write it as IO. So in this case IA. Okay. You can write this as half mvg square plus half ig omega square, or you could write it as half ia omega square. Remember? And the reason I wrote this formula is because this is rotation about fixed axis. Okay. Now I'm going to show you that this formula actually reduces to that formula. Okay, they're equivalent. I did it for a different problem. I did it for the spinning disk. So let's write this expression here. What is the inertia about A? Okay, it's Ig for the rod plus M. Let's say this is L, and let's call this as 2r. Okay, I write 2r because that's the diameter, and this is the 0.8 is the diameter. So this thing here is r. Okay, so I'm going to write it as Ig rod plus ml squared divided by 4 because this is half the length squared for parallel axis. Okay, that's not it. I need to find the inertia of the disk about A. So that's going to be Ig disk plus mass times plus, I'm going to continue next line, half Ig disk plus, it's going to be mass times the distance from the center of mass, which is here, all the way to here. So that's going to be L plus R. So M times L plus R square. Okay, so that is how I got the inertia using one of the formulas. I'll show you that I get the same answer if I use the other formula. Okay. Okay, so half mvg square. So in this case, there are 2 masses, right? There's mass disk and mass. Maybe I should have put it here. This is, okay, I need to make a correction here. This is M2 and this is M1, right? M2 and M1. Okay, Now this is going to be m2 times vg2, where vg2 is the velocity of the rod square, plus half m1 mass of the disk times vg1 square, velocity of the center of mass of the disk, plus for half ig omega square I have two inertias. There's one due to the rod, so I'll call that half igr omega square, plus half igd omega square. Okay, so it's still not, it doesn't look similar to the expression on the right, but all I need to do now in order to make it look like the expression on the right is to substitute vg2 and vg1 in terms of omega. Okay, so what is the relation between vg2 and omega? vg2 is the velocity of the center here. What's the velocity of the center of the rod as a function of omega? Remember we had done v equals omega cross r somewhere in the first chapter. So you're going to use that formula. Velocity of any point is velocity of another point. The formula was velocity of b is velocity of a plus omega class r b with respect to a. Okay. Now this is looks very complicated, but for the case when something is rotating about a hinge point, with one point is rest, this thing a is 0, and the velocity is always tangential, and the velocity is basically omega, the speed, times the length. So this is going to be omega times the length. So it's omega times the length from g2 all the way to a. So that's going to be L divided by 2. Okay? We can think of this as if it is like rolling. When it's rolling, when something is rolling, the velocity of the center is omega, the speed of the disk or the sphere, times the radius. In this case, it's like rolling about point. A is like the contact point, and point G2 is the center, is like the center of the disk. It's the same formula. Okay, and that formula really comes from this expression which I wrote here. Okay, Vg2 is that. Vg1 is the velocity of the center of mass of the disk. Okay, so velocity of the center of mass of the disk is going to be omega times the distance from the center all the way to the point which is fixed, which is A. So that distance from A to G2 is going to be L plus R. Okay. Okay, now if you try to sub in this over here and this over here, you should get the same expression as this. Can you see it? You should get the same expression. Okay, so let's see how that comes. So there's IGR, there's IGR, there's IGD, there's IGD. There is VG2 square, which is omega square L square divided by 4. So there's going to be L square, M2 times L square divided by 4, which is right here. Okay, and finally there's going to be VG1, which is omega times L plus R square, that comes over here. Okay, so if you sub that in, you should get the same expression on the right. Okay, intentionally did not write it down, but I wanted to go home and convince yourself that it's true. So no matter what formula you write, you get the same answer. Now there's another formula I gave you for general planar motion. Okay, if you apply that formula too, you'll get the same answer. Okay, because this is a special case of that general motion. Okay, so what you get from T2 is, so if you put the inertia of the rod, which is ml squared divided by 12, So IG disk is mr square divided by 2, and IG rod is ml square divided by 2l. If you put that in this expression here, everything else is given to you. What you get is 31.2 omega square. Okay, so we got T1, we got T2. It is in terms of omega square. All I'm left with U12. U12 is the work done by external forces. There are 1, 2, 3, 4, 5 external forces. Okay, H, V, M, M2, and M1. Okay, now the work done by HA and VA is going to be 0 because point A is fixed, it is not moving. Okay, so that makes it easy. So there are just 3 forces we need to consider. The effect of M. Okay, now M causes this to go from 0 all the way to 90. So the formula for the work done by moment is M times T theta. If you were to take the integral, M, which is the moment, times the displacement due to angular motion. So that's going to be pi by 2 minus 0. So the convention is a positive M causes theta to increase, and so that particular work done is positive. Okay, M is positive, and the angle goes from 0 to pi by 2, positive. The work done by M to G is going to be positive or negative. M to G acts downwards, and the pendulum is displaced downwards, so it's going to be positive. So it's going to be L divided by 2, right? Because when it goes 90 degrees, the distance moved is L divided by 2, plus M1G times the distance moved by the disk, center of the disk, L plus R. Okay, all these things are given. M1, M2, L, capital M comes out to be 312. So when you use the principle of work and energy 1, you get omega equals, well, you get square root of 10, which is 3.16 radians per second. Okay, so summarize. Draw the free body diagram. When you see that, you notice that you're going to find the velocity as a function of distance or displacement. You're better off with principle of work and energy. Write that and then find each of those quantities, T, U, and T2. Now, in this case, I showed you that you could use either formula for rotation about fixed axis. So when you choose T, there are 3 cases: pure translation, pure rotation, and the general planar motion. So you make your life easier if you can identify it to be a pure rotation or a pure translation problem, because there are simplified versions of planar motion. Once you get that, it's just a matter of crunching numbers. Any questions? Questions?